We're almost at the finish line. Let's test how our model performed. We start the testing part by finding the predictions. We can store them in y-hat test and use the reg predict method with argument xtest to compute them. Next, let's plot the test targets against the predicted targets and see if they resemble a 45-degree line. Wow, it looks quite decent, doesn't it? But there's even more to this plot than we see at first glance. Let's take a better look. For higher prices, we have a higher concentration of values around the 45-degree line. Therefore, our model is very good at predicting higher prices. However, for lower ones, the situation is not so amazing. They are much more scattered, pointing to the fact that we are not quite getting the prices right. We can include an additional argument to the scatter plot called alpha, which will show the proportional opacity of the points. Alpha takes values from 0 to 1, with 1 being the default. I'll set it to 0.2. You can fiddle with the value later on if you wish. This turns our graph into a heat map of sorts. The more saturated the color, the higher the concentration of points. The paler the color, the lower the concentration of points. Thus, we have a much clearer indication, showing most of the points are indeed very close to the 45-degree line. You must be wondering how good these predictions actually are. Well, let's get to that then. Although it's unconventional, we can manually explore what the algorithm came up with. This will give us yet more food for thought about what we've accomplished. I'll create a new data frame called DFPF, standing for Data Frame Performance. The data in it will consist of the predictions, so y-hat test, while the column name will be simply prediction. Okay. Unfortunately, these are the predictions for the log prices. Normally, we'd prefer the prices, not their logarithms. Since the log is the opposite of the exponential, if we take the exponentials of the log prices, we will reach the original prices. An easy way to achieve that is through the numpy exp method. Let's replace that in the DFPF declaration. Great! We now have the predictions expressed as prices. Right after that, we can place the targets, or y-test, next to them in the same data frame, so we can easily compare them. Let's put the exponential of y-test in DFPF target and check the result. Unfortunately, we have a lot of missing values, and they are quite randomly spread. To try to understand issues like this one, we can display the y-test data frame. What we notice is it contains indexes. In fact, when we split the data into train and test, the original indices were preserved. So, when we added y-test to DFPF, pandas tried to match the indices. What we need is to forget this original indexing. The easiest way to achieve that is to overwrite y-test with y-test reset index with an argument drop equals true. This operation will reset the index of y-test. All right. Let's overwrite the exponential of y-test in DFPF target. We get the result we initially tried to achieve. Okay, great! So, we have the predictions and the targets, and now we can proceed to comparing them. That can be done manually, or since we are coding, we could employ some code. Let's create another column named residual, which will be equal to the difference between the targets and the predictions. You can call it difference as well if you wish, but it would be precisely the residual. This whole data frame makes a lot of sense when evaluating the regression. The main reason is that the OLS framework is based on minimizing SSE, and that is achieved through minimizing the sum of squared residuals. Therefore, examining the residuals is the same as examining the heart of the optimization algorithm. Okay, in conclusion, I'll also add difference in percentages to make it extra easy for us to evaluate the outputs and the targets. Difference in percentages could be created in several different ways, but my preferred choice is to use the residual divided by target and multiply by 100 to reach a percentage. And one final tweak I'd like to make is to display the absolute difference in percentages. Whether an observation is off by plus 1% or minus 1% is mostly irrelevant. All right, we've got all that we need. To evaluate the aggregate performance, we could print the descriptive statistics of the data frame. Let's go through some highlights. The minimum difference in percentages is 0.06%. So the output was spot on. The maximum difference in percentages, however, is pretty off mark. Apart from the minimums and maximums, there are the percentiles. All of these tell us that for most of our predictions, we got relatively close. At this point, I'd advise manually visiting the data frame. Let's sort DFPF by difference in percentages using the sort values method. By default, Pandas doesn't show us the whole dataset. If we'd like to see all rows, we can set the Pandas display options to show 999 rows. In addition, to make the dataset more readable, we could change the display option for floats to 2 digits after the dot using this expression. Fantastic! Revising this data frame manually, we can see for which types of observations we've got good predictions and for which we are very far off. To me, it is particularly interesting to explore the ones that have the biggest differences. Going to the bottom of the data frame, we see that there are very few predictions dramatically far off from the observed values. If you look closely at the observed column, you notice that the observed prices are extremely low. $3,000, $4,500, $2,600, $1,700. As we know, our model is using the mileage, engine volume, brand, registration, and body type to predict the price of a used car. On average, it is pretty decent at predicting the price. For these last samples, though, it isn't. An important note is that all residuals for these outliers are negative. Therefore, their predictions are higher than the targets. An explanation may be that we are missing an important factor, which drives the price of a used car lower. It may be the model of the car which we removed at the beginning of the analysis, but it may also be that the car was damaged in some way, a piece of information we did not initially have. Okay, so there are different ways in which we can make our model better. We could use a different set of variables, we could remove a bigger part of the outlier observations, or use different kinds of transformations. The model we've just created is not outstanding. The creation of a truly great model for a certain problem may consume months or even years. Machine learning requires us to revisit the model many times before we are truly happy with the result. That said, feel free to dive into improving this model on your own. Thanks for watching.